What is big data and why is it important? Big data has become really the key core competency of the information age, what distinguishes the current era. And what is big data? It's really when the data is large enough that you really have to think about it, how you're going to organize it, how you're going to store it, how you're going to manage it in order to gain some benefit from it. For some organizations, this might be like hundreds of gigabytes. For others, it might be multi-terabytes or even getting up to petabytes, depending on their experience. Now, why does it matter? Well, big data can confer enormous competitive advantage for those who can make the most sense out of it and take actions based on what they're learning. Examples like Google and the Barack Obama campaign show when people use data, they can really stand out from what's around them and their competitors. As people have gotten used to using more data, what they've been finding is that data, the size of the data, becomes a key component in improving the quality of things like predictive models and recommendation engines and so forth. A good example is Google's use of their translation engine, which was improved not so much by a better algorithm, but by having so much data available. And we've been hearing this from across many industries that when you have a lot of data and you're able to incorporate that into decision making, everything comes out better. We talked to more than 30 people, vendors, users, other leading edge thinkers about big data, and crystallized some key technology dimensions that we're going to talk about. Some of these, there's even tensions between two choices, which direction you want to go in. So the first one would be one box or going parallel. We've talked a lot about parallel being the real option for big data. But for many, if their data isn't that big, there are single box options. What they really need to think about is, are there technologies that might work, for instance, column databases, or putting more engineering into their single database that can make that work for the size data they have, and thinking about Moore's law and that machines get bigger. The next thing is the style you're going to use. We've mentioned MapReduce a few times. Relational databases and SQL are the other options. And what we found is that it depends on your organization, your skill sets, kind of willingness to learn, how much infrastructure you have. So SQL is something that a lot of people know. There's a lot of infrastructure to support it. You probably have people who do know it and understand it. And that might be, in some ways, an easy choice. With MapReduce, there is some learning, but from everything we hear and know, it's a pretty quick learning curve. Requires a little bit more programming than maybe SQL does, but there are things happening that are making MapReduce easier to work with. What we found, though, is that people using MapReduce can be very engaged with the data. We don't know whether that's just because they're early adopters and are excited about using it, or if there's something inherent in MapReduce that just gets people more involved with the data. They also really can be complements. MapReduce is great for experimenting and trying out data that you're not really sure how it's going to be organized. Which brings up to organization of data, which is an important piece of the puzzle. One of the reasons people are using some of the alternative technologies is because they don't really know how they're going to use the data. Depending on your familiarity with the data you might want to be analyzing, in some cases a predefined schema where you know how you're going to use the data makes sense. In other cases where you're not really sure how you're going to use it, not defining the schema ends up being a great benefit. The type of data structure that allows you not to have to predefine your data includes these key value pairs, which are common with MapReduce and other simple databases. What these allow you to do is just kind of throw the data in, analyze it. When you figure out a repeatable pattern, then you can turn it into another data structure for repeated analysis. That decision can be very important for kind of new efforts or experimenting with data. We talked about having multiple machines, and when you start getting into parallelism, you start getting into needing to think about resiliency and failure handling. A lot of databases are designed around the notion that you're not going to have your hardware fail very often, and that there's a recovery process. As you add more nodes or more servers to the system you're using, you now are guaranteeing you're going to have failures, and maybe on a common basis. Then there's other kind of infrastructures that accommodate those failures readily. Now, something like Hadoop and MapReduce allows that handles failures very well, and some of the databases handle that as well. So, in thinking about your platform, you might want to be thinking about how many nodes you might be using and how important failure is to what's going on. On hardware, the two kind of main choices are whether you get an appliance, which has the software and hardware pre-configured for you, or whether you try to configure yourself. And a lot of that relies on what kind of resources you have, how quickly you want to get going. The appliances, some have proprietary hardware, and some use more off-the-shelf hardware, but know the configurations and have done some testing on what works. Some of that depends on how much parallelism you're going to use. If you're trying to keep the number of nodes constrained for cost reasons, the appliance approach might be a good one because there's testing and tuning done by the vendors. If you're really going to be going to a large number of vendors, it just might not matter as much because if there's a performance problem, you can just add more nodes to the platform you're working on. Now we're going to look a little at the future of what's going on with big data. First we're going to look at is hardware. One, the hardware is always getting better. The disks are getting more capacity. CPUs are getting faster. There's more and more cores, which makes parallelism a little easier. One of the things that's happening is more and more people are thinking about SSDs or solid-state disks. There are some limitations to them. There's a write limit that's based on physics. There's the expense. They're much more expensive than regular disks. But their prices are going down, and they can be a real game changer when performance matters more than anything else. So there's something to keep your eye on, and they might be an important part of what you might want to do with your platform. The next thing is compression. Compression comes up because the kind of conventional wisdom about databases is that they are disk-bound and that there's spare CPU cycles. What we've been hearing from the people who've been testing is that that isn't necessarily true, that when you do compression, it depends on the data, how much it lends itself to compression, and just the way you've got your system configured, how much CPU is handling how much disk. We actually do think compression will be used, but we think it'll be light compression algorithms that don't compress the data very much, but don't require very much CPU and work very quickly. The next thing is real-time. A lot of people think about real-time data as creating significant competitive advantages, and in certain circumstances that's very true. A couple ways to handle that real-time data are to use streams or wavelets. These are designs that take the data as it comes in and tries to quickly make sense of it and put in data structures that can be used. In the case of wavelets, these can be approximations, and you've got to decide whether approximate data values are good enough for what you're trying to accomplish. The last thing is a newfangled data structure called the triadic continuum. This also can handle real-time data and fast data processing. In fact, it's continually making kind of probability estimates of what's in the data as the data gets loaded. And this is something we're keeping our eye on. It's still in a pretty early phase. Just to wrap things up, we've talked about a couple of technologies and some of what's going on with databases. What we think is going to be on to handle big data is you're going to use a mix of technologies. It's going to depend on the type of data, the skill set of your engineers and analysts and consumers of data, your budgets and so forth. But that you probably will be mixing things together based on ability and on your desire to be engaged with the data. And that's something we'd recommend, is that when you can do something to engage more of the organization's data, become more of a data-driven company, embrace that experimental approach where nothing is going to stay static, but you're going to keep trying new things with the data. We think that what can happen is that you actually turn data into more of a solution than a problem. If you want to learn more, we do have a big data report that goes into more details about the technology choices, and on the next slide you'll be able to see the URL information to order that report.